what factoring does for these types of problems, excuse me, is that you are starting with what is called a quadratic. You're starting with something that looks like that. That's what you call a quadratic equation. A quadratic equation is an equation that has a second degree exponent. What that means is there's an exponent of 2. Okay? That's called quadratic. When I write it out in terms of what's A, B, and C, that's called standard form. And when you guys learned about this stuff last year in Algebra 1, what you guys learned was that these quadratic equations generated parabolas. Okay? They were up like a cup shaped or they were down like a frown shaped, depending upon certain things that were going on with these equations. Now, when you got into that, what you guys learned was by taking specific parts of the coefficients, you were able to do something like this, and you had this, what was called an axis of symmetry. That axis of symmetry, yes ma'am?
Are we supposed to learn this stuff before this?
Yes.
I don't remember any.
So what happens here is that this axis of symmetry basically cuts the graph into 2 equal parts. If you take a line down your face, your face is technically symmetrical unless you've got a broken nose or something, but one half is on one side, the other half is on the other. It's the same idea with what we're calling parabolas, quadratics. What happens here is with this so-called axis of symmetry means that any point that is on this side is equidistant from it's what we call symmetric twin on the other side. It makes those values the same. And it works at the bottom all the way on up and up. Okay? That's what these things do. What you learned from that was that eventually, somewhere, these graphs sometimes crossed over the x-axis. When they crossed over the x-axis, that meant that the value of, the value of y in the ordered pairs was 0. When you cross an x-axis, your value of y is 0 here. If you cross the y-axis, your value of x is 0 because that's 0 there. So what you did was when you first learned how to do this, it was very inefficient. You guys went through the whole process and you graphed these. As you graphed a parabola, trying to see if I can just make something up here. Bless you. As you learn to graph a parabola, you learn that where it crossed the x-axis, we called those zeros. Okay? So in an example like this from last year, you would have said that your zeros of this, what we call function, the zeros were at -4 and +1. That meant in the equation, whatever the equation was for this quadratic, this parabola, if you will, if you substitute in -4 or you substitute in +1, your equation would equal 0 at the end. You were going to ask Mr. Hill?
I was going to say, you know how we were doing that, what is it, like the T-chart thingy?
Yeah.
That's how you get those numbers, right?
Not so much yes, in so many words, yes. It's when we started with graphing of stuff, we learned that there's more efficient ways to do things. Graphing is a very nice visual way to do stuff, but being able to solve for specific, what we call zeros, and solve for parts on equations, it's easier to do things algebraically. Take this back even further still. You guys talked about parabolas probably beginning of second semester last year, I want to say. Yeah, sometimes June second semester. But if you go back to first semester your freshman year, you guys had stuff like this where, remember when you guys graphed equations? Let's say you graphed y equals negative 2x plus 1 and y equals 3x minus 4. Let's say you had these two equations, and what they were asking you to do was solve for the intersection point. Do you guys vaguely remember doing that? You figure out where they run into each other? So if you did that, when you graphed, you'd start at your, remember the whole y equals mx plus b? You'd start at your b value at 1. You go down 2 over 1, down 2 over 1, and so on. And you graphed your first line. And then you would do that again with the secondary equation. Start at negative 4, go up 3 over 1, and you do this one. And you found where the two lines intersected. Those two lines intersected at what we call an ordered pair, a solution set. The solution set for this problem would have been 1, negative 1. That's your x and that's your y. When you did that via graphing, it took forever. Because you had to make sure where things lined up, you had to make sure your lines were straight, and you see where all your points matched out. But a lot of times, some of these things didn't land on a specific singular point. They might have been at a fractional point. So what you learned then was the next step in the natural progression of solving these equations. You learned how to solve what's called a system of equations, okay? So here, if you go back and think about it, you have y equaling two different things, which means these two things have to be equal. Remember how we talked about substitution steps at the beginning of this semester? So each school year, you're kind of doing the same thing, but then just different topics. So via substitution, you guys learned that you could do this. Negative 2x plus 1 equals 3x minus 4. Add 4, and you get x equals 1. You take that value, you go back in here, and you get y equals negative 1, which we found graphically. It was always quicker and more efficient to do stuff via algebra than it was graphing. So most topics that you guys learn about in geometry, or in algebra really, if you graph them first, which more often than not you do, there's usually a different way to find answers via the algebra. That's kind of what factoring is. Instead of graphing all these equations all day long and figuring out where they cross the x-axis, by factoring them, you're figuring out where they cross the x-axis by figuring out what the factored terms are. And I do this a lot with my hands to show parentheses for terms, because when you factor like a trinomial, three-part thing, or a quadratic, or any what we call nth degree polynomial, which you'll talk about next year in Algebra 2. You could factor something that has x to the 5th, something that has x to the 6th. It's all the same basic principles of figuring out where do these graphs cross the x-axis. Actually, the idea of where things cross the x-axis is quite literally what they call the fundamental theorem of algebra. If you have a second degree polynomial, how many possible zeros could you have? 2. If you have a third degree polynomial, how many possible zeros can you have? 3. If you have a 7th degree polynomial, how many possible zeros can you have? Thank you for learning how to count to 7. That was pretty scary for a second there. And that's the basic idea for most of these things, okay? When you have a first degree polynomial, that's 3x minus 4. How many times does that cross the x-axis? Once, okay? So the idea that you can do these things is all boiled down to just that idea, that statement of what's called the fundamental theorem of algebra. We talk all about that in first semester of Algebra 2, but you're using the same basic ideas of how do you take a trinomial and break it into smaller parts, okay? So what I want to kind of do here is show you guys what happens when you start taking, what exactly, I'm going to do this, a couple really easy ones, and then kind of build into some of the trickier ones like you saw with, you know, you had leading term coefficients that weren't equal to 1. But I want to do a, why does this work, and what does this mean to factor and find a 0? Okay, because I think that's where, I don't think the idea of taking the geometry part, chunk times chunk equals chunk times chunk, is difficult. You could write that out all day long. When it gets down to it, you're like, okay, now what the hell do I do? And that's where I think you guys are at the hump of, correct me if I'm wrong.
You're right.
All right. What's that? No, I want to work on this, because if we can get this straight, which I believe we can do with just a little brief refresher on a lot of things, we can tie it back into the geometry stuff again. Okay, and I'm hoping that you take this seriously, because this is stuff that you will have on the test. This does not go away, and I know you guys are struggling a little bit with this. That's why I wanted to kind of throw the brakes and kind of re-explain what exactly is happening. What does it actually mean, okay? So if I'm looking at one like this, and I have x squared, minus a 3x minus 4. You guys came through the school system in a time frame in which they changed so many different what are called algorithms for solving equations, especially factoring. An algorithm is just a mathematical process. All right, and you've probably heard that before, I'm thinking, right? So an algorithm is just a process of doing something. It's just a very do this, do this, do this, do this. It's a very regimented way of doing something. What they did a lot of times with you guys is that over the course of your schooling, probably starting around 4th, 5th grade, they started showing you guys multiple ways to do things. They showed you guys multiple ways to multiply. They showed you guys a bunch of different ways for division. They showed you, like you just said, lattice. They showed box methods and stuff like that. But here's the problem, Nigel. There's nothing wrong with lattice, but you can't do it with fractions and you can't do it with decimals. But here's the thing. In Algebra 2, there are many sections where we don't allow calculators. And you have to know how to do these things. There's a lot of stuff that takes too much time to use the calculator when you're dealing with fractions, because all you have to do is multiply by a reciprocal and you can do that quickly. That's where I'm getting at, though, because unfortunately you guys kind of had a little bit of a disadvantage because of the way the education process was going. It has its peaks and valleys with a lot of stuff. Whereas I grew up in an era where, back in my day, it was drill and kill. And you guys heard that before, right?
No.
Drill and kill. Drill and kill is basically you're doing times tables until you cry.
That's actually cool.
What's he?
Times tables.
Well, he's a math teacher. He knows what he's doing.
And the idea was that they made it a point back then. They made it a really big point back then to make sure that the fundamentals were beaten into your head into submission. So that way you can go through and you know what times what's 48 that adds together to get, or what times what's negative 48 to add together to get negative 8 or something along those lines. You could do things like that because you knew your what are called factors. And unfortunately, you guys weren't basically brought up in the idea of drill and kill. It wasn't so much of a skill that they believed as necessary. They wanted you guys to see the ideas and find your way through it and figure your own way, because they wanted the independent thought part, which is fine. But in the back of your mind, you still have to have that what times what equals something, okay? So the way that I always approach factoring, I am, yes sir?
X is 4.
Okay, let me get to it in a second.
It was so
What happens here is that I am really old school when it comes back down to factoring. I always go back to one method and one method only. I multiply my tails. First of all, what's the coefficient of x squared that you don't see? 1. Remember you guys what coefficient means? It means number in front of variable.
Yeah.
There's a 1 here that you don't see. So I am still multiplying my tails. What's 1 times the negative 4? Negative 4. So what I'm doing here is I'm trying to figure out what are my multiples of negative 4 that add together to get negative 3. Well, when you're thinking about multiples of 4, think of that not as multiples, but I'm sorry, I should say factors. 1 times 4, 2 times 2. That's all there are for that. Obviously, when you're multiplying two numbers together to become negative, one of the numbers needs to be negative. You have to then figure out to decipher which of the two numbers has to be negative. Well, since this one we know is not going to work, but since this number is the negative, that means the bigger of the two has to be.
Yeah.
So it has to be negative 4. Yes, sir?
It could have been 8 times 0.5.
If it's 8 times 0.5, what does 8 plus 0.5 equal? It doesn't equal negative 3, does it?
I was just saying that
Usually what we do, and I know where you're getting with it, you're right, because technically there's going to be infinite values and factors. We're looking at whole numbers. Okay.
I was giving a suggestion
So what happens here is that since your first term isn't going to, or I'm sorry, your first coefficient is 1, you can automatically write down what are called your terms. Your terms are things that I always refer to as the bits in parentheses. Terms generate zeros, okay? So this is going to be x minus 4 and x plus 1. It doesn't matter which number you put first, because when you multiply it all out, it all ends up the same anyway. Yes, ma'am?
So after we factor, we don't even have to go back to that, this whole like thing is,
No, because what you're doing is you're breaking this, what's called a trinomial, into two binomials, okay? Because then if you wanted to check if you're right, you would FOIL the whole thing out, and it should equal that and go backwards. Okay, so what you're doing is you're unfoiling it, all right?
Yeah, Mr. Murphy. Would you get the one?
What's that? Which one, this one?
It's X.
Oh, this one here?
No, down there. Yeah.
Okay,
From there?
from here. What are your factors of 4? 1 times 4?
Yeah.
2 times 2. 1 times negative 4 is negative 4. 1 plus negative 4 is negative 3.
Yeah.
That's where I got the 1. So now, when you're trying to, the difference between a problem that says factor versus the difference between that says solve, your solved problems always have an equal sign. So basically what happens is you do all of your factoring like you would normally, but at the end you have one last step, or one last step. You take both of your terms, the things in parentheses, and you set them both equal to 0. Because what you're doing here is, if either one of those values of x generates a term of 0, when you multiply it out, it will always equal 0. So 4 minus what? Or excuse me, x minus 4 is 0. So what is x? What minus 4 is 0? 4. You just add the 4 over, you get 4. On the other side, you get what? Negative 1. So algebraically, I'm not even worried about that right now. I'm just talking algebra. We're not back in geometry land yet. Sounds like a great theme park. I bet you they have signs everywhere.
Haha! That was a good one. That was a good one.
It was pretty bad.
yeah.
He was overly excited on that one. It wasn't that good. So what this means, guys, what this means is that
Mr. Murphy, you could get a tan, Jim.
go away.
You can get a 10.
So what this means is that if I use either 4 or -1 in the equation for x, the equation will equal 0. Okay? That means that this graph, if you graphed it, I don't know, I know it's going to be up because the first one's positive, it would look something like that. That's what all of that means. When you're factoring something out, you're taking that, what we call a trinomial, or basically any, what's called an nth degree polynomial, and you're breaking it into smaller chunks that can be set equal to 0.
Kill it. I can't wait to go to Geo.
All right?
Geo. I bet you have the best one because
All right?
They're all just parabolas.
Yeah.
yeah.
They have their ups and downs.
He's on fire.
He on
So I pick this man
He's
up.
on the road.
Anyway,
Back to the math. Because that's what
same idea. You have the same basic idea, guys. And what I want you guys to see here is that even though the numbers get larger and signs can get mixed around and whatnot, the process by which you go through it doesn't change. It doesn't. You're still going to get the same, you still go through the same questions. You're still asking the same bits. The first term is x squared, but what's the number in front of the x squared you don't see? 1. So I'm still going to multiply my tails. What's 1 times 88? 88. So multiples of 8, what are the factors of 88 that I add together to get 19?
1 times 88.
Yeah. You have a 1, 88, a 2, 44, 3 won't work, 4, an 11, 5 doesn't work, 6 doesn't work.
I thought, no, it's 4 and 22, not 4 and 11.
Wait, the third
Oh,
doesn't
sorry.
work. It's a decimal.
Right. Right. Do you guys know the trick for finding 3s? What's 8 plus 8?
16.
Does 3 go into 16?
Yeah.
Then it won't work.
What?
You didn't know that?
No, we're not.
No.
Genius.
No, it's a trick. It's a trick for figuring out multiples. If you take two numbers, if you take any of those numbers and you add them together, if the numbers add up to something that's divisible by 3, then that number is divisible by 3. 88 isn't divisible by 3 because 8 plus 8 is 16. But what about 87? Well, what's 8 plus 7? It's 15 divisible by 3. Yeah. So that means if I divide this by 3, 3 goes into 8 twice, and how many do you have left over? You have 2, and you have 9. That's how that works. Okay? That's how that stuff works. 4s go if, I think it's if 2 and 3 works, 4 works. 5s work if the number ends in a 5 or a 0. 6s I forgot. There's some reason, some rule. I don't remember, but 10, that's an easy one. It ends in a 0, okay? So just by quickly at this, yeah, wait till it gets past 9. For this one then, which of the combinations work? Guys, the bottom one. The bottom one. And this one works. They're both positives, so you don't have to worry about any of that. So you write it out. X plus 8, x plus 11, and that generates a 0. So that means,
both positive.
change the sign, right? Because see how this one was 1 times positive 88?
Yeah.
That adds the positive 19. That means both numbers are positive. Okay. So, guys, again, that means you're doing this to figure out what are your generated zeros. Factoring creates terms. Terms generate zeros. That's how the vocabulary for this stuff works. Okay? In this case, you're both your zeros are negative, and that's perfectly fine.
Okay.
Remember, we're not in geometry land, we're in algebra land.
Oh, okay.
So if we were in geometry, then it wouldn't work.
Algebra
It
is
could.
kind of boring.
It could, yeah.
It's for smaller kids that are.
You know, you heard them making the algebra too? Yeah.
Ah,
You
got
got
you.
you.
That was good. I'll give him that one. That was good.
That was
I'll
good.
give him that one.
Go get him that baby. Come on, Mary. Go on.
Oh, I do this. Going along to this.
Mr. Murphy,
Yes, sir.
can I use my bathroom pass?
Yes, fine.
Thank you all.
All right, same deal. Take it the next complex part to it. When you go through, what's up, Rod? Take the next idea of the complex part to it. When that first term is no longer equal to 1. When your first term has a different, what we call coefficient. In this case, my coefficient is now what? 5. Guys. Well, what's happening here is since we have to, what's 1 plus 88? Yeah. Not 19. What's 2 plus 44? Not 19. What's 4 plus 22? That's what we're trying to do. Multiples of this that add to that.
Okay.
Okay.
So then 11 plus 6
Last time I checked, that means you're 2.
Oh, okay.
And that's when the terms come in.
All right.
Okay. All right. So now, guys, this is where most of you guys screw up. I want to make sure this is where you have to really make sure you're keeping up on it. Each of the 2 previous problems, we've still multiplied 1 times the back number. So now instead of a 1 at the first number, what is it? It's a 5. So I do 5 times 6.
5 times
It's still giving me 30, but I'm saying all the steps.
Oh, yeah.
I'm still multiplying my,
Nigel.
guys,
I didn't have to look.
I'm still multiplying my tails. I'm multiplying my tails together to get positive 30, but I want them to add together to equal negative 13.
Yeah.
Now that tells you 2 things. Well, it actually tells you 1 thing. If I multiply 2 numbers together that are positive, and then I add those 2 numbers together and it's negative, what do those 2 numbers have to be? They both have to be negative. The reason that they both have to be negative is because negative times negative is always positive. Negative plus negative is always negative.
Whoa. So,
That's why that works.
okay, so I right. I was nervous that if I would have changed the sign for both of these.
No?
And then is it like, oh, I just skipped all of them.
And that's fine.
I went straight to negative 10 plus negative.
And this is, and the idea here, these are all negative. Okay?
Yeah, it's 3 times 6.
Ladies and gentlemen, that just means, as you look at your list, it has to be the negative 3 and negative 10. Because negative 3 plus negative 10 is negative 13. So here's our winner. Now, the way that we work with trinomials that have the first term not equal to 1, we do it just ever so differently. What I like to do is called split middle term, or some people call it factor by grouping. So what I'm doing here is I'm going to take these 3 pieces and turn it into 4 pieces. And how I do that is because I know that negative 3 and negative 10 creates the negative 13. So I just put them in order. 5x squared minus 3x minus 10x plus 6 is 0. Because now, since I have 4 terms, or sorry, 4 parts to the problem, I can group them in pairs. That's the trick when this first number is not a 1. When that's not a 1, you break it into 4 parts. So you throw parentheses around the first. Now you're just, when you do that, you are just looking for GCN. What does a 5x squared and a 3x have in common? And the x, right. So I can factor out an x. And I'm left with 5x minus 3. On the next one, this is the little bit of a goofy step here. Do you see how the third part is negative 10x plus 6? What I like to do here, let me rewrite this real quick.
Should we rewrite this?
No, I just wanted to move it over. I do this, plus a minus, and then I group it with the minus on the inside of the parentheses. The reason that I do that is because then it forces me to remember to bring it out. More often than not, that's a step that you guys will mix up, and one of your signs gets screwed up. So if your third term is ever subtraction, rewrite it as a plus minus. So now, if you're looking at that, think of it in terms of 10 and 6. What does a 10 and 6 have in common? A 2. But I need to take out a negative 2. If I take out a negative 2, what's negative 10 divided by negative 2?
5.
5. What's 6 divided by negative 2? Negative 3. So now, are the two things you have in parentheses the same? That's a good sign. If those two are the same, you want to write it down. What's left?
X is negative 2.
And you're done.
So that's a easier one?
That's the way that, I wouldn't say it's the easier way. It actually is about a step or two longer than some other methods, but it always works. Whereas some of the other methods, you might get against the thing, oh, I can't do it that way, I can try another way. So if this takes an extra 15, 20 seconds to do, it's worth it because it will always work, all right? This is the only method that I ever use. I still use it in my Honors Algebra 2 class. And you figure those guys have seen, and they're good at all the other methods, but this will always, always work, no matter what, all right? So now you have your two terms, so you set each of them equal to 0. When you set those both equal to 0, one of them is really quick to solve for, the one on the right. What minus 2 is 0? Well, 2. Okay. On the other one, you have to add the 3 and divide by the 5. And I think we had an example yesterday in class where one of the terms was, oh, I don't know, let's say it was 3x minus 4. I just said out loud, add 4, divide by 3. It's kind of where you get those things. Okay? So that's how you go through, and it does look like it's a lot of work, but it's a very visual way of setting yourself up to get factored terms, to get what we call zeros. Okay? So when you look at, excuse me, when you look at, where was it? There we go. When we look at, which one was it? Crap, the number was 9, no, 7. So when you tie it back into, guys, when you tie it back into a geometry problem then, this is that outside hole, which meant that it was 5 times 12 is x times x plus 4. So if you tie this all back together, what the geometry part is having you do is create the quadratic equation. Create what we call that trinomial, that second degree polynomial, by using some of the definitions that we talked about, the outside hole in this case. Multiplying out, you get 60, x squared, and a 4x. Which means then, you have to set aside equal to 0.
Oh, yeah. Move the 60.
Can you
Move the 60, yeah. So if I move the 60 over, and some people were asking me this yesterday and actually today, does it matter what side the 0 winds up on? It doesn't. It can be on either. It doesn't make a difference at all.
So why do you minus 60?
What's that? Because, oh, why do I subtract 60? Because the rule is that in order to solve one of these trinomial, or this quadratic equation, an nth degree polynomial, you have to have a side equal to 0 in order to factor. Okay? So here, you're asking what times what is negative 60, but it adds to 4. So you go through 1, 60, 2, 30, 3, 20, 4, 15, 5, 12, 6, and 10.
Isn't there a way to do it on the calculator?
I don't know if this one has a table function.
It has to be the big blue one, right?
So obviously it's going to be the combination of 6 and 10. Which one of those is negative? Which? Yes, and why is the 6 negative?
Because the 10 is higher than 4, right?
Right, because the 4 is positive, so you want the bigger number to be that. Good. So your answer here, since your first value is a 1, would be x minus 6, x plus 10 is 0. So you're using the factoring, guys, to get to the geometry. This generates, these terms generate zeros at, well,
6 and negative
6 and negative 10. And can I have segment, and now back to geometry, can I have segment length that's negative?
10. No.
No. So your answer is 6. That's what we're doing, guys. That's why we factor to build into this, okay?
Thank you.
Did that help?
Yes, a lot.
Actually, yeah, that actually.
A lot.
Let me give you guys some more of these that have a little bit more of the factors tonight. We'll go over this again tomorrow.
So are we just keeping the last?
Yes, sir. What's that? Yeah. Let me give you guys, it's not all of this, so.
I know. My watch is oh my god, it was so ugly. I just think it's so ugly.
On this sheet, guys, do this on a separate sheet of paper so you have room to do some of the factoring. Ladies and gentlemen, what did I just say, Riley?
Separate sheet so we can know the factory.
Thanks, Riley. Guys, do this stuff on a separate sheet of paper so you have space to do the work. The first couple are pretty quick, but it's also, remember, it's one of your 3 things from yesterday, so you're going to want to rewrite those 3 generic formulas. Chunk times chunk equals chunk times chunk. Outside hole equals outside hole. Tangent squared equals outside hole. Okay? Make sure you write those out and go through them. The backside's going to have the factoring to it. Some of it has factoring, but not all of it. Okay?
Not all, guys.
What's up? No, I didn't quite. Apparently we all forgot how to factor, so I thought it would be a good idea to spend time on that. Hopefully it works.